single phase half controlled rectifier with RLE load. So far we have seen single phase half wave control rectifier with R load, RL load, and now for RLE load. The same circuit diagram, one more load is going to get added to this. What is the circuit diagram? Initially it will be having a transformer. So transformer will be 4. Okay. What is the switch we are using here? What is the three-phase circuit? Thyristor. So it will be having 3 terminals, that is gate, anode, cathode. So here what are the loads we are going to add up? Resistive, inductive, and E load, RL, E. This E can be any voltage source. We can use it by a battery, or else by the when will the back EMF created when will be back EMF created? In where? It will create in the motor, right? So that is by the back EMF that is created by a DC motor. We can use it that back EMF over here, or else we have to connect a battery over here. Okay, so that is RLE. What is the E? This is the voltage we are connecting using a battery, or else the back EMF which we are getting by the DC motor. Okay, that voltage we are going to give here. So this is a battery voltage or the back EMF of a DC motor. Back EMF of DC motor. So now, normal working principle. What supply we are giving here? AC supply. So what is the voltage? What is Vs? Vs is equal to Vm sin omega t. Okay. So during first half cycle goes through the anode cathode during the forward condition. What is the voltage should be? How the input voltage should be? Should not be greater than the forward blocking and the reverse blocking rating of the thyristor. The input voltage which you are giving should not be greater than the forward blocking and the reverse blocking voltage of the thyristor. So that particular voltage will flow through the load, R load, L load, and E load. Okay, what happens if this load is connected to a control rectifier? How will be our waveforms? Okay, so initially, what is our input voltage here? Sine voltage. So that is normal. V S, that is input voltage, that is Vm sin omega t. Okay, so with respect to omega t. So next, we will be giving what? When will be the conduction starts? When will the conduction starts? Here. When will the thyristor will turn on? Gate voltages will be, when the gate pulsar, we will be saying it that is firing angle alpha. When it is given, the thyristor will turn on. So that alpha. Okay. First half cycle, and this is from 0 to pi. Here 2 pi goes up to 3 pi, and here once more this is the second item, firing angle alpha with respect to omega t. Okay, and now how will be our output voltage? Okay, here the same what we have seen for resistive load. Initially there won't be any voltage. Okay, after the firing angle is given, the thyristor will turn on. So the load will have increase the voltage level. After that it reaches some maximum value. Okay, so after that it comes to the 0. Okay, so next who is present here? This is for resistive load, right? Next to the load is who's here? Inductance. What is the nature of inductance? It will store some value of current. Okay, so due to the storage of current, what will happen? It won't be zero. It will go till the thyristor is in the shut-down condition. So till the it will reach to the negative side of the voltage value. Okay, so this rating is said to be what?
Beta.
Beta. Okay, so this is phi and the second is beta. So now, what is the next load here? E back EMF or else a battery voltage is still there. Okay, so will it be remains in zero then? Since there is a voltage there is, so it is going to be sustained for at that E value. Okay, so this is the nature of resistive load, and this beta is the nature of inductive load, and this is the back EMF voltage that is going to remain. So until when it remains, until the next firing angle, that is next firing angle. When it is going to, until the cycle when it remains until first 2 pi. Okay. So here once more it is going to be alpha, right? So until when it remains 2 pi plus, this is 2 pi, right? So this is alpha means 2 pi plus alpha. This E will sustain up to 2 pi plus alpha. Again the voltage will increases due to the firing angle. Again the resistive load condition is going to happen. That is after that again the inductive inductive nature will happen. Again the back EMF nature will happen. The cycle will continue. Here, initially the voltage is 0 at the point of 0. Due to the resistive load, what happens? The voltage will reach to the maximum. After that, it will reduces to 0. Due to the inductance nature, inductance will store some sort of current so that it won't go, the thyristor will not turn off. So what is happening? Till the conduction is happening in the reverse blocking stage. So it will go to the negative half cycle. Okay, so that region is beta. After that, due to the presence of the E, which is a connected battery voltage source or also back EMF of a DC motor, what is happening? The voltage is not in the zero. It is having that battery voltage or as a back EMF voltage that is going to sustain up to 2 pi plus alpha. What is this value? 2 pi plus alpha. Okay. Again the resistive load nature, again the inductive nature, again the back EMF nature. This is going to continue. Okay. So now this is the output voltage with respect to omega t. Clear? Next, how will be the output current with respect to omega t? So like this, till the firing angle given it remains 0. Okay, that is the output current will remain output current I naught. Okay, it will remain 0. After what will happen? Due to the inductance nature, the current will not drastically increase as like the resistive load because inductance is storing some sort of energy current over there. So what will happen? It will increases drastically, slightly. Okay, so after reaching a maximum point, it will reaches to 0. When it will reaches at the beta point. Okay. So after that, it will remain 0. During the next half cycle, it is going to increase. After that, at the beta point, it will decrease. Okay. So this is the output current with respect to omega t. Okay. So that is all about the RL load waveform. After that, what you have to know? We have to derive the average DC voltage which is being converted. Okay, so that is VDC is equal to, what is the formula? For the complete cycle we will be seeing it. So 1 by 2 pi. Okay, so here, what are the integral? What are the voltage sources here? First from where it is happening? From
0 to
alpha 2. Conduction starts from alpha. So from it is happening to alpha to beta. So alpha to beta, what voltage is here? Vm sin omega t alone, right? So that is Vm sin omega t d of omega t. Okay, along with that, who is there? One more battery is
Beta.
there, right? So battery starts
Beta
from beta to
to 2 pi plus alpha.
2 pi plus
Alpha.
alpha. Who is there? E. With respect to what?
Omega t.
D omega t. Okay, so now shall we take integral down? So the constant is 1 by 2 pi. If I take Vm constant outside, it can be like
Vm by
Vm by 2 pi. So if we integrate sin omega t, it is
minus cos omega.
minus cos
Omega.
omega t. What is the limit where is from? Alpha to beta. Okay, so likewise plus what is here? E is constant, right? So E is constant. I am integrating omega t, it will become 1 into omega t, it will become omega t.
Beta.
So the limit ranges from beta to
2 pi plus
2 pi plus alpha. Okay, so while substituting the limit, it will be like Vm by
2 pi
2 pi into.
minus
So if you substitute upper limit, what is that? Minus cos beta minus of minus cos alpha plus E into what is upper limit?
2
2 pi plus alpha, lower limit minus beta. Upper limit minus lower limit is the case for integrating, right? So now we can write this as Vm by 2 pi. I can write this as minus of minus, it will become plus, right? So first we are going to write the plus cos alpha minus cos beta. We are going to write as the second term plus E into what is here? 2 pi plus alpha minus beta. This is the output VDC. Okay, so what is an IDC then? You copy it. So far we know that VDC is equal to what? Ohm's law, V equal to I into R. So VDC is equal to IDC into R. Since that is having a resistive here in the load. Okay, so now along the resistance, who is here? E. Okay, because E also is there. So VDC is equal to IDC into R plus E. Okay, so we want to find out average DC output voltage. So we will be giving VDC minus E is equal to IDC into R. So if I write it again to the left hand side towards the right hand side means how it will become? IDC into R is equal to VDC minus E. So what is an average DC output current is? VDC minus E divided by R. That's it. Okay. So this is the formula for the output DC current and this is the formula for the output DC voltage. Okay. So that is all about single phase half control rectifier with RLD load. After drawing the circuit diagram, what you have to say? And omega t is equal to 0. There won't be any voltage. When the firing angle is given, the SCR will turn on. Okay. So during the firing angle alpha, that is what happens. The firing angle once alpha is given, the SCR will turn on, so that output voltage will be reaching to a maximum value. After that, it will 0. Okay. So after that, due to the inductance in nature, there is some storage current is there. So due to that, the thyristor is still in the turn on condition. It is not off. So that it will go to the reverse blocking state condition. So that it will be reaches towards the beta. And due to the RE battery or else a back EMF in the DC current, so DC motor, what is happening? It is still sustained in that E voltage. It will not be in the 0. So it will happen up to 2 pi till the next alpha is triggering pulse is given. There is 2 pi plus alpha. So since the next triggering pulse is given, the same cycle will continue again. So for the current, it will be 0 till the alpha. Since due to the inductance nature, it will increases to slowly. Okay, so it increases slowly and it reaches to its maximum value and it will be 0 only at the point of beta. Okay, so after that it will be 0 till the next firing angle alpha is given. So next firing angle alpha is given. So that is it. We have to describe it with respect to working principle. When alpha omega t is 0, what is happening? when omega t is alpha equal to alpha, what is happening, how the switching nature is, and when omega t is equal to beta, how the switching nature is. Okay, so during a working principle, you have to describe this and you have to draw the circuit diagram and you have to derive the average DC output voltage as well as the DC output current. This is easy, okay. So average DC output voltage, two cases. One is during the alpha to
Beta.
beta. What is the voltage switch here? Vm sin omega t. The next cycle is from the beta to 2 pi plus alpha. Here the voltage is E. After taking the integral, substituting the upper limit and lower limit formula, we have gained that VDC is equal to Vm by 2 pi into cos alpha minus cos beta plus E into 2 pi plus alpha minus beta. And for current, VDC, we know that VDC is equal to IDC into R plus E, because one more battery sources voltage is here, we have to add that also plus E. So after that adding that, VDC minus E is equal to IDC into R. So that IDC we can write it left hand side and right hand side in the other mode. Next IDC is equal to ADC minus E by R. This is the average DC output current. Okay, so that is all about the single phase half control rectifier. We have seen it for R load. Its average output voltage as well as the average DC output current we have seen. Likewise for RL load also the same circuit diagram with RL load, its waveform. Then up to it stands up to beta. Okay, so next for that same we have derived average output DC voltage, average output DC current. Now we have seen single phase half control with RL E load and its waveform, and it sustained up to the first cycle to beta, the second cycle from beta to 2 pi plus alpha. For that we have derived average output DC voltage, average output DC current. Okay, that is all about single phase half wave control rectifier. Hereafter we will be seeing about full wave control rectifier, similar for this all three loads: R load, RL load, RLE load. Same for RLE load. Same likewise for three phase RLE load we will be discussing. Okay. The next is single phase full control rectifier with R load. So for R load we have seen it full control rectifier. Okay, so we are going to give a AC supply. We are be using 4 thyristors. Okay, here we will be using 4 thyristors. Just note on how to draw the circuit diagram. We will be having resistance as the load initially. Okay, this is R. First thyristor will be having 3 terminals, that is 8, 1, so I am naming this as thyristor number 1 and this is thyristor number 2. So this is 8, 2. Okay. And I am naming this as thyristor number 3. So I am taking this as gate signal 3. Okay. So this is thyristor 4. So I am naming this as gate number 4. Okay. So first input terminal phase I am connecting to the first wire. The next neutral I am connecting to the over here. Second. Over this side. Okay. I am just jumped over here and I am connected to the next terminal. Okay. That is neutral. So now if you look at the diagram, it can conduct at both the half cycle. That is, for half wave control it conducted only in the one quadrant, right? So we have seen for half wave control how it is. It is your I naught and this is your V naught. During the only during the positive half cycle it is conducted. Both the voltage as well as the current is in the positive half cycle. Okay, this is for half wave control rectifier. So for full wave control rectifier, it can conduct, okay, both in the positive half cycle as well as in the negative half cycle. That is, we can say that 2-quadrant operation. We can say a fully controlled rectifier as a 2-quadrant operation system. That is, V naught can either be positive, it can either be negative. Okay, with respect to the output current. But what about output current? This only
Positive.
positive. Okay, so output current is only positive. Voltage either it is being a forward bias condition or sorry, either it can be a positive half cycle or it can be a negative half cycle. It will conduct. Okay, so how this is happening? Look at the cycle diagram. I will tell you. Now during positive half cycle. Okay, from phase 2. Okay, from phase 2, who is going to conduct here? Can this be conducted? No, it is reverse, right? So who is going to be conducted? T1. Okay, so from T1, next where it goes? Will it conduct? No. So next where it going to go?
Resist.
To the resistor. From the resistor, which circuit it will conduct?
T2.
T2. From T2, the circuit will close towards neutral. So during the positive half cycle, from the phase 2, thyristor 1 will turn on. Once the gate signal IG1 is given, when the firing angle given to the gate source 1, what will happen? Thyristor T1 will on. Okay, once it is on, next it is going to flow towards the resistive load R. Okay, from there it is going to flow through the thyristor 2 over here. Okay, so from there it is going to neutral. If you look at this, from phase 2 T1 to resistance R, from resistance R to T2, from T2 to neutral. You clear with it? So the next mode of operation during negative half cycle. Okay, so that is negative half cycle. Negative half cycle means the reverse of it, right? So from neutral to. So from neutral to neutral is over the second point, right? Here from second point which is forward to T3. Okay, from T3 to R resisted load. From the next T4 to T4 is connected to whom? Here it is connected, right? So this direction. Phase. Okay, so that is from neutral to. I have drawn it in green color. Okay, from neutral to T3 is connected. Once the gate signal G3 is given to the resistive load R, then to T4 and again to phase. Okay, phase. Clear? So that is from neutral to T3 to the resistive load R, then to T4, then to phase. Okay, this is the positive half cycle operation and this is the negative half scale operation. Clear? So now the voltage source conduction and the output DC voltage remains in both the positive half cycle and the negative half cycle. So how will be the waveform then?
Both positive and negative.
Will be the voltage source. So now the same AC voltage we are given. Let us be in with respect to omega t. The same alpha firing angle is we are going to given, to which we are going to given, that is the thing. So the first firing angle we are giving to IG1 and G2. Okay, so that is why alpha second half cycle. These two are positive, right?
Yes.
Positive half cycle. T1 and T2 is conducting, so gate 1 and gate 2. Okay, so the next alpha, here also alpha, positive half cycle. Next G3 and G4. G3 and G4 will comes in the negative half cycle, right? So negative half cycle. So during the negative half cycle also, you will be drawing, there will be a alpha firing angle. So this is the alpha firing angle for positive half cycle and alpha firing angle for negative half cycle with respect to omega t. Clear? Can you able to understand, follow me? The next is output voltage source with respect to omega t. Okay, the same half control rectifier operation only. The same for resistive load only. During positive half cycle, what is going to happen? Initially, the voltage will remain 0. Okay, after some alpha firing angle is given, it is going to rise and it is going to increase. Okay, so up to where it remains, here this is 0 to pi and here it is 2 pi. Up to the 5. Okay, and it will be remains 0. Next firing angle is given for the gate 3. So it is going to conduct in the negative half cycle also. In the half wave control rectifier, there won't be any conduction in the negative half cycle. In fully controlled rectifier, we have used 4 thyristors. The first half cycle T1 and T2 is going to conduct, and in the second half cycle T3 and T4 is going to conduct. Can you able to understand me why I am naming it as T1, T2, T3, T4? It will be easy for you to expect as well. Okay, and now the next during the negative half cycle, again the voltage is going to rise and it remains 0 at the next cycle 2 pi. Again the next positive half cycle, it will rise once the alpha is given and it wants to remain 0 at 3 pi. Okay, and this is the output voltage for the respect to omega t. And how will be the output current for the resistive load? How did I told you? This output voltage and the output current will be in the in phase condition. Both will not be in the change. Okay, so it will also going to be 0 initially. There is no inductance nature, just a resistive load. How the voltage is going to be, the same will be the current. So it will initially rise and it will be going to remain 0 at the 5 and it will sustain 0 at till the next alpha is given. Okay, so it will going to increase and going to be 0 at the point 2 pi. Again it is going to be 0 till the next firing angle is given and it is going to be 0 at the 3 pi. This is the output current with respect to omega t. So that is all about single phase full control rectifier with R load. For this, we have to derive the average DC output voltage for average DC output current, and we will be generating for RMS voltage also. We will be deriving that we can see in the next class. Okay. For now, we just note out the circuit diagram. Draw the principle of operation for the write down the principle of operation for the both positive half cycle and negative half cycle. Then draw the graph. So last class we have discussed this. Take your note and take a glance of it. Single phase fully controlled rectifier with R load. You remember, for fully controlled, how many thyristors we have used? Look at the circuit diagram and tell me, for a fully controlled, how many thyristors we have used?
2 thyristors.
Fully controlled converter. It is not 2.
4 thyristors.
4 thyristors will be connected like this. Okay, so we have to derive the output voltage in terms of RMS also. For that I am drawing the circuit diagram again. And once more I will be giving the class 2. Okay, so this is for all our loading, so all load, and here the gate signal. We will be using 4 thyristors. Okay, so the thyristor having 3 terminals. Next experiment also we have done, that is anode, cathode, gate. So when the SCR will turn on, when the triggering pulse is given. Triggering pulse is given to the terminal gate. Okay, when gate pulse is given, I will be saying that firing angle is given. So this is your input source. Okay, we are connecting RPS. Okay, so we will be raising the range of RPS up to 0 to 30 volt. Okay, regulator power supply. So 2 modes of how will we give, or else if it is the experiment, we will be giving it as plus minus. Okay, so here we are studying in terms of, in theory we will be doing it in AC. That is our phase which is connected over here and the neutral to the second terminal. And I am naming this thyristor as T1 and this thyristor is right opposite to it. Okay, it's right crisscross opposite. Okay, so it is thyristor 2, and here it is thyristor 3, and this is thyristor number 4. Why I am naming this? There is here it is the input is AC input. Two half cycles are there. One is positive half cycle and negative half cycle. In half control rectifier, okay. In half control rectifier, it will act only in the positive half cycle. That is during the when voltage as well as current both are will be in the voltage as well as the output current both will be in the positive side. So single quadrant, you can say that half control rectifier is a single quadrant operation rectifier. Okay. Whereas in fully controlled converter, the current will either only in the positive, whereas the voltage will be either always in the positive as well as in the negative half cycle. So all this introduction I have given last class. Okay. For your understanding, I am saying it again. So that is. So now, during positive half cycle and negative half cycle, two modes of operation there. So we will first time we will be taking this phase and neutral. Okay. So first condition, that is the operation during positive half cycle. So whenever AC supply is given between this phase and neutral, what happens during positive half cycle? The thyristor T1 is in the forward bias condition. Whenever a gate signal, okay, the gate triggering pulse is given to the gate terminal, what happens? This thyristor will turn on. Okay, so through this thyristor, the current flows through the resistive or load. Okay, so from there, both the thyristors are in the forward conduction only. Either the current can flow to I2, T2, or else the current can flow to T4. Both are in the forward condition. But when the circuit will close, if it is close to T4, will it connect to neutral again? No. So it is because T4 is connected to phase. Okay, the circuit will not close. Okay, it will get short circuit. So what happens? The current will flow through the T2 towards the neutral. So we can say that during positive half cycle, the flow of current from phase to thyristor T1 next to the R load and next to the thyristor T2 and next to the neutral. Okay, this is during operation during positive half cycle. Okay, and the next operation that is during the negative half cycle. So negative half cycle is the reverse of it. The neutral to phase. Okay, that is 0 to pi operation over. Now pi to 2 pi. Okay, so the current will flow from neutral. So neutral means which thyristor is in the forward condition? Thyristor T3. When the gate pulse is given to the thyristor T3, from the neutral the current will flow through the T3, which will be in the turn on condition. So from T3 to the current again flows through the R load, resistive load. Next the current will flow through the, which will when will the circuit close, the current flows through the T4 back to the phase. This is from neutral to phase. Okay, so this is for the negative half cycle. Okay, so when this process will be successful means when both the thyristor will turn on in a right same time. Okay, everything is happening with respect to what? I have drawn this graph with respect to what? Time t, right? With time t. So if only the thyristor, the triggering pulse which I am giving for T1 as well as the triggering pulse which I am giving over here for T2, if it remains same, then only this operation will be more successful. Yeah, the turn on time, or we can say that the triggering pulse that they are giving, the firing angle. The firing angle is represented by the letter alpha. Firing angle. What is the purpose of firing angle? Once the firing angle is given to the terminal gate, the thyristor will turn on in the forward bias condition. Okay, or we can say that once the SCR is triggered, it will turn on. Okay, so for turning on of the thyristor, they are giving the firing angle. That firing angle is represented by the letter alpha. So this alpha, it will be in the form of some degrees. Okay, so that is either from 0 to pi means pi is how much degree? 180 degree. 2 pi means 360 degree. Between this one full cycle is 360 degree. Okay, so halfway control rectifier means it will work out in the first half cycle. So 180 degree. Okay, so full way control we will be saying that as 2 pi. Okay, for complete cycle we will be taking in 2 pi. Okay, so halfway control rectifier we have taken the complete complete cycle. During positive cycle, the conduction is there. During negative cycle, no conduction, it remains zero. Though, if you see the graph, if you go through the graph, it will remain zero. Okay. So for fully control, how is the graph we have seen? So you can take like this. Okay. So positive half cycle, negative half cycle, again a positive half cycle. Okay. So if this is your input voltage, and here we are using the supply voltage, that is AC, and we can represent it as Vm sin omega t, as like that in the half wave control rectifier. With respect to whom we are deriving with respect to time omega t. Okay. And now entire thing is this is the angle, right? So now this is full wave control. So the next, whenever I am full wave control rectifier, the thyristor during positive half cycle, the thyristor T1 and T2 is turn on condition. During negative half cycle, thyristor T3 and T4 is in the turn on condition. So on both the half cycles, the operation is going to be done. So the voltage waveform is going to be continuous, as not like the half control rectifier. In half control rectifier, what is happening? Only during the positive half cycle the conduction is there. In the negative half cycle, what is happening? It remains zero. Okay, both the current waveform as well as the voltage waveform, if you look at it remains zero during the negative half cycle. But in fully controlled rectifier, both in the positive half cycle and during the negative half cycle, the conduction is continuous. Okay, so for the continuous conduction, what we are using? We are using 4 thyristors. The next is T1 and T2 is in the on condition, the other 2 thyristors will be in the off condition. Okay, so during negative half cycle, T3 and T4 will be in the on condition, the other 2 thyristors T1 T2 will be in the off condition. That point also should be mentioned. Okay, so now once the alpha is given, okay, so this is, if you are taking this as a firing angle alpha with respect to time. So I am generating this as the, if I am taking alpha is some 30 degree. Okay, this is pi, right? 0, pi, 2 pi, a complete positive as well as a negative half cycle, 0 to 2 pi. So in that particular, what I am taking alpha as 30 degree. Okay, if I take 30 degree, what about the next? So this is during the positive half cycle I am taking, and I am saying this at this condition T1 and T2 is in the on mode. Okay, and during this condition I am taking alpha at whenever T3 and T4 is in the on state. Okay, so during this T4 and T3 on state, this will be negative half cycle. Okay, so the T3 and T4, this firing angle will be given to them. Okay, the firing angle will be given to the gate terminals of T3 as well as the T4. During the alpha condition will be in the negative half cycle condition. Okay, so likewise during the next half cycle, that is from the positive half cycle. Okay, this is when which is the firing alpha will be in the next cycles. Okay, the next positive cycle. That's T1 and T2. This will continuous. Okay, this will continue. So then how will be our output voltage waveform? Our output voltage waveform is thyristor voltage will be, or output voltage will be 0 initially. Once alpha is given over here, right? Once it is given, okay, once alpha is given, thyristor will turn on, so that output voltage is started rising. After some point it reaches a maximum value, and after some point it reaches to 0. When it reaches to 0, at pi comes to 0. Again during negative half cycle, one more alpha signal is given to the thyristor T3 and T4. Right? So at that point it will be remain 0. After that, during the alpha during the turn on conditions of the T3 and T4, again the voltage will flow till 2 pi. Okay, till 2 pi. This is the alpha means. Okay, till 2 pi. This is 2 pi. This is pi, and from alpha. Clear? And next alpha, next cycle. Again T1 and T2 will be the on condition. next lesson, next again T1 and T2 will be in the on condition. Okay, so again this will continue up to 3 pi. The cycle will carry. The same for the output current. Okay, the same load will be remain 0 after the firing angle the current flow remains 0. After for R load it will be in phase both in the half controlled rectifier R load and in the fully controlled rectifier R load. The voltage, output voltage and the output current will be in the in phase condition. As like how the voltage, the same will be the current. Okay, so when it nature changes means if there is any storage load. Next we will be seeing about the RL load, that is inductive in nature. So inductive will store some sort of current over there. Okay, so at that condition there will be some changes. Till that for resistive load there won't be any changes. The current and voltage will be in the in phase condition. Okay, so the same for the current load. Everything happens with respect to omega t, angular frequency and time. Clear? And now we have to realize. So I have taught this already last class, but for derivation we require this. Okay. So first what we have to derive? We have to derive the average load voltage, or we can say that output voltage, average DC voltage. What is here? This is purpose of rectifier circuit. From what we are doing here, we are converting this AC to DC. Now if you see that everything is in the positive half cycle, right? So in positive, how is the DC waveform? The direct current. Okay. So we need to achieve the direct straight current. Here what is happening? Ripples are there. Okay. So why we are changing the load? This is R load, right? So we are next cycle we are going for RL load. So we are going for RL load for that purpose also. In inductive nature, for due to some storage of current, what is happening is the ripples can be reduced. If you see the resistive load, these are what? How should be the direct current with respect to it should be almost it should be like this, right? But there is some ripples. It is reaching to till 0. Okay, maximum we should not reach 0. We should the current flow should be direct. Okay, so first we will be calculating the average load current, or we can say that average DC voltage. Average load voltage, or we can say that average DC voltage. So in half control rectifier, what we have seen the full cycle. Okay, during positive as well as negative, because negative it remains 0. So we have taken complete full cycle. That is, we have taken the derivation as 1/2 pi. Do you remember? Now for fully controlled rectifier, the changes happens for all the pi. From 0 to pi there is a changes. Again negative half cycle is also continuing. So pi to 2 pi is also the some amount of operation is happening. Again 2 pi to 3 pi also is happening, because due to the resistor on condition. T1 and T2 is on during 0 to pi. That is alpha to pi. Once the firing angle is given, alpha to pi. Okay, and again T3 and T4 is on. Then pi plus alpha to 2 pi. Can you able to follow me? From alpha to pi only T1 and T2 is in the on condition. This state is what? Pi plus alpha. So pi plus alpha to 2 pi, 2 is on condition. T3 and T4 is in the on condition. Again from 2 pi plus alpha to, okay, 2 pi plus alpha to 3 pi, who is in the on condition? T1 and T2. Can you able to follow me now? During from when omega t is 0, there won't be any conduction. No direction is going to on. Once the triggering pulse alpha is given, the direction is going to on. So during positive option, we are giving it firing angle to T1 and T2. That is in the forward conduction mode, right? So it is getting on. Okay. So the on period is omega t is alpha to pi. That is for positive half cycle. For negative half cycle, pi plus alpha to 2 pi. So this will continue. Okay. So for the one cycle is happening for changes is pi. So we will be writing it as 1/2 pi. Okay. So whenever we need to find out some value, we know the lower limit and upper limit. What form of calculation we will be going? Mathematically, we will be going for integral calculus. Okay. 11th we have studied. Why we are going for integral calculus? Okay. omega t, and then we should derive with respect to p of omega t. Okay, and that is equal to 1 by pi. Pm is constant, right? So I can take Pm outside. When I integrate sin omega t in this, minus cos omega t, minus cos omega t, and the limit ranges from alpha to pi. Clear up to this? Next, 1 by pi. Instead that we can write it as Pm by pi. Okay, so if we substitute upper limit minus cos, instead of omega t I can write pi. Upper limit minus of, already the term has a minus, upper limit minus lower limit. Clear up to this? Now shall I interchange it and write Pm by pi into, I can write the plus term first, right? Minus into will become plus cos alpha. This term will go straight. It is minus cos pi. What is cos pi value? We need to know in trigonometry, and we need to know integral, everything. Okay, for electronics derivation. Cos pi value is minus. What is cos 0 first?
1.
Cos 0 1 means what about cos pi then? Minus 1. Because 0 1 means the same next term outside 180 degrees minus 1. So we can write it as cos alpha. Already there is a minus over here, and cos pi is minus 1. Okay, so we can write it as how? Pm by pi. Shall I write the plus pi first? Plus 1 the first. Minus will happen? Plus 1. So I am writing the 1 first. 1 plus cos alpha. This is your average DC output voltage. Okay, so what is for current? What is the Ohm's law? VDC we have found out Pm by pi. So in division there is going to be 1 R. Pm by pi into R into 1 plus cos alpha. This is your average output DC current. Okay. So RMS load voltage means we have to take the root mean square of the voltage. What the voltage we have found out? Pm by pi into 1 plus cos alpha. So I can say that VDC, we have to come from VDC. Okay. So VDC is equal to 1 by pi integral of alpha to pi Vm sin omega t d omega t. Right. So the next. So what we are going to do? We have to take the root of the entire thing square. Okay. There will be a root mean square now. What is the coefficient? Square the whole root. If it is like this, root of a square. It will be like this. Root, what is the root mean square of a means? What, how will we calculate? Root of a square, which we calculate. Right? So we have done 1 by pi integral of alpha to pi. So Vm square sin square omega t d of omega t the whole power 1 by 2. So here we can take the omega. Sorry, we can take the Vm square outside, this constant, right? So I am taking out of the integral. So it will become Vm square by pi integral of alpha to pi. 2 will be inside sin square omega t d of omega t the whole power 1 by 2. Okay, so the whole power 1 by 2 is here. Here Vm square is there. Shall I take Vm outside then? Vm. Because Vm square and this power 1 by 2 it will get cancelled. So I can take Vm out of the square root. Clear? So now I can write it as Vm into 1 by 2. Integral of alpha to pi. What is the value formula for sin square omega t? Trigonometry formula for sin square omega t is
1 plus cos
1 plus
1 minus cos
1 minus
cos
1 minus cos
2 omega
2 omega t
by 1 by 2.
2. Okay, so you know the trigonometry. You should know the trigonometry formula. Sin square theta is equal to 1 minus cos 2 theta divided by 2. Sin square theta is equal to 1 minus cos 2 theta divided by 2. So I can write sin square omega t as 1 minus cos 2 omega t by 2. Okay. So integral d omega t the whole power 1 by 2. Remaining things follows. So the next that is Vm into 1 by 5. Okay. So here how can we write? Shall I take this 2 common outside here? So I can write it as 1 by 2 pi. Right? So the integral is from alpha to pi. What will remain inside then? 1 minus
cos 2 omega t
cos 2 omega t d omega t. The whole power 1 by 2. Here after this next thing. Vm into 1 by 2 pi. Shall I integrate it now? If I integrate 1, it will become whom we are with respect to whom we are integrating omega t. So 1 omega t is integral of 1 omega dt. Integral of x dx is equal to integral of 1 dx is equal to
x.
x. Then integral of 1 into d of omega t will become
Omega t.
omega t. That's it. So 1 we can write it as omega t. Okay. So here minus cos 2 omega t is it. Integral of cos 2 omega t. What is 2 cos theta?
Minus 2 sin omega.
No. Sin
Sin 2 omega t.
okay. Sin 2 omega t by
By 2.
okay. Sin 2 omega t by 2. Okay. The coefficient of x term will come to the denominator. Okay. So the limit varies from alpha to pi. Okay. The whole power 1 by 2. This bracket is round bracket and the whole bracket should be a square. Clear? So now Vm is equal to Vm into 1 by 2 pi. The first term upper limit minus lower limit it will become pi minus alpha. Okay. So the next root is here minus of here sin 2 pi sin 2 pi minus sin 2 alpha divided by whole power 1 by 2. Clear? So the next that is Vm into 1 by 2 pi. This will be there pi minus alpha. Here shall I write it? If I multiply this minus inside this term will become minus and this term will become plus. Shall I rearrange it, right? So it will be like this. How it will be?
Sin 2 alpha.
This will become plus, right? Because I am going to multiply this. So it will become sin
2 alpha
2 alpha
minus sin 2
minus sin 2 pi
by 2.
by 2. The whole power 1 by 2. Next, Vm into 1 by 2 pi of pi minus alpha plus who is here? Sin 2 alpha. What is sin 2 pi?
0.
0. Sin pi is 0. So sin 2 pi will also be 0. So sin 2 alpha divided by
2
the whole power 1 by 2. That is equal to Vm into 1 by 2 pi. Okay. Shall I multiply this 2 pi inside? Okay. 1 by 2 pi I can write it as 1 term of right? So that will become
Pi minus
alpha divided by 2 pi
plus
plus
sin 2 alpha divided by 4
pi. The whole power
1 by 2.
1 by 2. This is what we output in terms of RMS. Average or RMS root mean square value of the load voltage. And what is for current then? Current I naught RMS will be equal to
V RMS divided by R.
V naught RMS by
R.
capital R. So it is resistive. So that's why we not what is the I autonomous then?
VM by R.
Bm
Vm
by R
by R into
5
5 minus
minus
5 minus alpha plus sin 2 alpha divided by, sorry, here is also there is 2 by 4 by whole power
1 by
1
2.
by 2. That is all about fully controlled factors R. First you have to know the circuit diagram. Next you have to explain the principle of operation with along with the omega t value. What if omega t is 0? What if omega t is alpha? What if omega t is pi? What if omega t is pi plus alpha? The entire operation you have to describe it. Then you have to draw the graph. After drawing the graph, you have to derive the average load voltage, average load current, average load RMS voltage, average load RMS current. Clear?